and welcome. Today we're going to be going over the history of interferometry. We're going to be covering a classic Michelson-Morley setup and Dayton Miller's work and the subsequent experiments and modern technology that have reproduced these experiments and we're going to go over their findings and all that stuff, right? So we're going to look at the progression and the history of things. So I have here some papers or some clips from papers of the apparatuses and stuff that they used so we can get a look at what they were doing here. And we have some diagrams to go along to explain what all these things are right here. So we have the mirror configuration set up here. We have our coherent light beam. We have where the beam is split and recombined. And that's also where you take your observations through here. So the lighting in here is not great, but this is an eyepiece telescope situation that you look through here and you look at the fringe patterns while somebody your lab assistant holds basically like a yardstick out that has like a little ruler attached to it, and they take their readings, right, against the fringe, and you look at that to get your to get where it's lined up and take your measurements. Oh, they also had a copper wire situation that they would place over it to like mark the readings or whatever, so they could go back and measure the distance more accurately. So it sounds like pretty crazy. It's like, wow, how accurate can you get with that? Well, it turns out pretty dang accurate. So starting off with that, so that was their basis, that was their jumping off point. And then of course with electromagnetic propagation, I agree with you about illumination stuff being instantaneous and all that. But the fact of the matter is, electrical engineering is based off of Maxwell's equations and the rate of induction and all that, and you are able to make very accurate predictions based off of that. You're even able to find the refractive index of different materials and mediums based on that variance and see that all comes from that's all derived from Maxwell's equation. So when they talk about the speed of light, that what they're really talking about is any electromagnetic propagation is fixed to that speed roughly, right? That's their baseline thinking, because that's the general approximation that's really accurate. That's good enough for pretty much all the stuff, except when you get into these really, really fine, precise measurements is where we're going to start to see that C actually has a variance to it. And that variance is actually what facilitates them to, utilize technology based on that variance to make really accurate measurements. So here we have a more better a diagram. Let me see if I can expand that a little bit. Okay, cool. Yeah, so we have a diagram here that's better equipped with the lighting situation. So we got the mirror configuration here, beam splitter, beam recombiner, beam coherent beam emitter, right? And then we have our optical viewing device, right? Our telescope essentially, right? Or magnification to look through here and look at the fringe patterns against this. And then we have our other guy with his ruler situation, holding out the measuring stick and lining it up, right? Yeah, so here's a topographical view of what that would look like with the coherent beam source emitting its light, and then it does its thing, hits its beams, splits, reflects back, recombines here, and then you look at it through this device here, take your readings, right? Okay. So here's what they would have been looking at. I think this one specifically is from Miller's apparatus, but Miller's was based off of Morley's and stuff. So the French shift patterns in that regard would be identical. So this is what they would have been looking at here when they get through this eyepiece, right? And then you can see the different levels of magnification, so you can get your accuracy. And then also when you're calibrating the device, right? So when you take your measurements and when you get your mirrors all orientated correctly, and you could do that. We'll watch a video of how that's done here in a little bit. Based off of the size of these beams, when you're calibrating it, you can adjust these mirrors. And when you get the exact configuration that you took your first measurements in, again, that's how you know that you've realigned it correctly and all that. So it's, it seems like a bit sketchy. It's like you got a guy with a yardstick with a with a ruler attached to it, essentially, in such a way that they could line it up to this and take their measurements. Like, it sounds crazy. How accurate can you get? Well, really, really accurate. So here is an apparatus that Miller built, and he had this in the basement in the what's it cool case study physics school or something like that, or case physics school. I can't remember the name, but something like that. Oh, case school right here. That's it. Anyway, so we had this in the basement here in one of the sections. This was the apparatus, or an apparatus that he built to do control studies. So he would like figure out what all affects the what affects the readings. How what makes these fringe patterns increase or decrease accordingly, right? Um, so he went to work on that. So he had another apparatus as well. I think this is from the same one though. This is just with the thing removed. Let's see. And then this is with the housing on it, so that to cut down on what's it called, temperature variations and stuff in the room and in the air and all that, on the path of the beam that it's traveling on. This is the observatory for the Mount Wilson observation site, where he had an interferometer set up in there. This is the interferometer. So this is the one that he had set up that he took the actual readings from. So this was the control apparatus, and then he would come here to his observatory at altitude and take readings, and he found that he got stronger readings. Let's see here. So when you're looking at this, he got thicker readings. You could say it that way. He got more clear readings when he was at altitude. So based on his readings on the season, on the equinoxes, Miller's work, not Michelson-Morley. This is Miller's work for this one. So based on Miller's work, the way that he modeled out the fluctuation changes, and based on the assumption that Earth is a sphere and it's axially tilted, and that the sun's ecliptic, and and all that, right? Or that the sun's tilt is responsible for all that, right? So he modeled out what would be, the NLMA, right? Basically, what produces that? What produces the NLMA? So that's what he thought he was modeling. Now, heliocentrism denies this, even though this would be an excellent supplemental proof to heliocentrism. But the problem is that the fringe shift pattern here, if the Earth were traveling at 30 kilometers a second, they would have got much, much thicker readings. And when I say much, much thicker, like, these are really, really tiny measurements. So saying much, much thicker is like, it's not going to be like, insane, right? But it was outside of the purview of this, right? So we'll take a look at some modern setups. So this is a smaller configuration, but I think this is from somebody's YouTube video or just Google results. But just a very, very straightforward setup, nothing too fancy. Oh wait, that's actually from the PDF. This is just a modern one. Let's see. So Michelson-Morley setup is using an experiment to indicate the units as noted above. Okay. So here we have some circular fringe patterns. So this is a different type of fringe pattern produced in modern stuff when you're using a laser beam instead of just a coherent light beam source. So again, the thickness of those beam patterns is what they're looking at, right? So now we'll read a little bit from how Michelson-Morley took their measurements, and then we'll watch a couple of videos on the modern renditions of it. So this is from Michelson-Morley's 1887 paper. The observations were conducted as follows. Around the cast iron trough, there were 16 equidistant marks. The apparatus revolved very slowly, one turn in 6 minutes. After a few minutes, the cross wire of the micrometer was set on the clearest of the interference fringes at the instance of passing one of all the marks. The motion was so slow that this could be done readily and accurately. The reading of the screw head on the micrometer was noted, and the very slight gradual impulse was given to keep up with the motion of the stone. On the passing of the second mark, the same process was repeated, and this would be continued till the apparatus had completed 6 revolutions. It was found that by keeping the apparatus in a slow, uniform motion, the results were much more uniform and consistent than when the stone was brought to rest for every observation. The effects of the strain could be noted at least half a minute after the stone came to a rest, and during this time, effects or effective change in temperature came into action. The following tables give the means of the 6 readings in the so this just goes into the data sets. So we'll read this out. So the following table gives the means of the 6 readings, and the first for the observations made near noon, the second those made near 6 o'clock in the evening. The readings are divisions of the screw heads. The readings are divisions of the screw heads. The widths of the fringes varied from 40 to 60 divisions. The means of the values near 50. So 1 division means 0.02 wavelengths. The rotation of observations was, so let's see. So here's their data recordings for their noon observations and all that. So the thickness of the beam, they have these marked here. They were expecting it to be, that thick, right? That was going to be the thickness of their readings, the beam or the fringe width, right? And they got just over 1 fringe, and they were going to correspond each thickness section, right? Like how they divvied it up, they were going to correspond that each to 5 kilometers a second for their scale of interpretation. So let's see here. In what precedes, only the orbital motion of the Earth is considered. If this combination with the motion of the Earth, the solar system, excuse me, 1 second, I have to cough. I apologize. All right, let's see here. In what precedes, so this is the end review of their paper, Michelson-Morley. In what precedes, only the orbital motion of the Earth is considered. If this is combined with the motion of the solar system concerning which but little is known with certainty, the result would have been modified, and it is just possible that the resultant velocity at the same time of the observation was small, though the chances of it are much against that. The experiment will therefore be repeated at intervals of 3 months, and thus uncertainty will be avoided. It appears from all that precedes reasonably certain that if there be any relative motion between the Earth and the luminiferous ether, it must be small, quite enough entirely to refute Fresnel's explanation of aberration. And I do not recall Fresnel's explanation off the top of my head, but I think it was in reference to a stationary ether or something like that. Because all these guys had different variations of stationary ether theories to explain various phenomenon that were coming up, and then they would fail to explain some other type of phenomenon, etc. And so they would have this like failing ether theory, but it was all facilitated by trying to view it through the lens of how to interpret Earth's motion through that stationary ether. So that could be a big reason as to why they were not getting accurate theories, that were more unified. So their fundamental baseline of the structure that they were building on was off. So Stokes has given a theory of aberration which assumes an ether at the Earth's surface to be at rest with regard to the latter, and only requires in addition that the relative velocity have a potential, but Lorentz shows that these conditions are incompatible. Lorentz then proposed a modification which combines the ideas of Stokes and Fresnel's, which assumes the existence of a potential together with Fresnel's coefficient. If now it were legitimate to conclude that or conclude from the present work that the ether is at rest with regards to the Earth's surface. According to Lorentz, there could not be a velocity potential in his own theory fails. So this is in regards to length contraction with Earth's motion and all that. So they're saying there was a friendship pattern, but even if they apply their all their best stationary ether theories together, they got nothing to show that the Earth actually has a velocity, right? Because part of the mechanics of an ether background, right, all motion being relative to the ether in an absolute reference frame, and mathematically and physically, like what that means is you would all motion would be relative to that ether wind, right? So electromagnetic propagation isn't just going to be, it's not just traveling at the same speed to you, right? And then your motion is relative to that speed of light. No, no, no. Your motion is relative to the ether wind, and electromagnetic propagation is relative to that, is just relative to your relative motion to the ether. So that's why the speed of light is the delay in which the receiver gets the information is proportional to the velocity of the observer. And you can find that in GPS, where they explicitly note that the, what's it called? That how I just worded it, that the velocity of the observer, like, so a signal receiver is a GPS signal receiver that's in motion. Um, the delay in which the signal is received is proportional to their velocity. That was noted by Wang in I forget the year, but that was in his analysis of GPS and special relativity, where he found that how they're taking these measurements and all that, that the speed of light is shown to vary and it's proportional to the velocity of the observer. So so that's the Michelson-Morley paper. So we read there, so how they were taking their readings. So they had a cross wire to mark the fringes, and then they would go back and measure it with a forget where it was where they talked about the rod. Oh, right here. Sorry, let me read this real quick too. I apologize. Let's see. Okay, so the lengths of the two paths were measured by a wooden rod reaching diagonally from mirror to mirror, the distance being read from a small steel scale, tenths of a millimeter. Okay, so they basically just had a little, ruler at the end of a wooden rod, and they would, reach over the apparatus with that, line it up, take their fringe measurements, and do their thing, right? So okay, so now we're going to look at some modern renditions of that. So this guy's channel, and I'll have links to all these in the description as well, so people can take a look. So this guy's channel is awesome. He has, now he is a globe lad. He is an ether lad, but he has his own apparatuses and takes his own measurements, and reproduces the Sagnac effect and Michelson-Gale, which were done. Sagnac was in 1913 and Michelson-Gale was in 1925. Both claim to measure Earth rotation relative to the variance in the speed of light that changes relative to the latitude, right? So you know how they say you're on a globe that's spinning 1,000 miles an hour at the equator, and then at the 45th latitude, for example, you'd be spinning at 750 miles an hour. Well, the speed of light, they're saying, varies relative to that latitude, where you're at, right? So due to that, due to Earth rotation. So this guy has built some apparatuses that seem to measure that fluctuation. What the cause of it is, we'll get into towards the end of it. I don't want to have to keep interjecting, my philosophy or whatever onto it. But we'll go ahead and look at this guy who built apparatuses that reproduce the effects that were measured in, the late 1800s and early 1900s. And then this is done obviously with modern technology here. So shout out to your boy Plenum 88. So this is okay. I'll just let him kind of skip through it a little bit. But so let's see. Oops. So this apparatus is what we call a classic or a Sagnac interferometer, right? So this is a fiber optic cable in a circular configuration It's orientated north-south, and then east and west is going to be along this axis. And the way that he has it orientated is so the way that they say that they get the best readings for the Sagnac effect for the variance in the speed of light relative to the latitude due to the motion of the Earth's rotation, right? The way that they say they get the best readings is when is on a single axis gyro. Now, this is what you would consider a single axis gyro, right? Um, so for a single axis gyro, the best way to get the readings is it has to be aligned with the axis of rotation, the axis of motion, right? So on a globe, they say that you would tilt it, to be in a line. The Earth is tilted on, it's a ball, but it's tilted, 23 degrees or 23 point, whatever it is, degrees off axis, right? So you have to align your device with Polaris, essentially. That's what they do. They say that aligning it with Polaris is equivalent to aligning it parallel to Earth's axis of rotation, and that's what produces the best reading. So that's what he's doing here. So he's got the z-axis of this device orientated to Polaris, right? So I'll let him explain that through, and we'll watch
vertically with respect to the rotating.
Let this play out here.
For a Sagnac interferometer to experience the full rotation of the Earth, we have to align it.
Oops, his audio is a little low. Let's see here.
In this figure here. This is the completed Sagnac interferometer. It is on equatorial mount, so it can be positioned in any direction horizontally or vertically with respect to the rotation.
Yeah, his audio is so low, I can't play it on 2x. Sorry, I'm just low. Sorry.
Vertically with respect to the rotating Earth.
Okay, god dang it. I'm sorry. Okay.
Direction horizontally or vertically. This is the completed Sagnac interferometer. It is on equatorial mount, so it can be positioned in any direction horizontally or vertically with respect to the rotating Earth. For our Sagnac interferometer to experience the full rotation of the Earth, we have to align it so that its z-axis is parallel to the North Pole. Once it's in this alignment, which is shown in the figure here, it experiences the full rotation of the Earth at 1 revolution per day. If, however, we turn the device perpendicular to the axis of the pole as shown here, it will experience no rotation at all. In this next graphic of the Earth, you can see the two orientations of the Sagnac interferometer, the one with the axis parallel to the North Pole.
Okay, so the big proof that they say of these gyroscopes, meaning the single axis, not necessarily the inertial guidance systems like in boats and planes and stuff, because those are multi-axis gyros, so those actually don't require a reorientation of the device to take a reading or whatnot. It will just average out the readings based on an additional gyroscope per each XYZ axis. But anyway, so they say that based on a globe to keep your device in alignment, you have to tilt it to be parallel to Earth's axis of rotation, and therefore that tilt angle is proof that we're on a globe, right? But what they're actually doing is they're making planar correction at 45 degree planar correction angles to Polaris, right? This is what we're going to see here.
One that will experience the most rotation, and the one with the axis perpendicular, the one that will experience no rotation. And we choose these two because we're going to flip between each orientation so that we can see the maximum change in fringe shift from one orientation to the other. These are just some pictures showing the Sagnac interferometer in some actual orientations. This first one is with the z-axis parallel to the North Pole, so it should show the maximum rotation. The second one is showing...
So at his latitude, by the way, he's around the 45th latitude. He was in Canada. He had it shown on the globe thing earlier. So anyway, he's got a 45 degree to Polaris, and then to pull up these labs real quick. So this is a single axis gyroscope lab in Italy. I think this one is. Yeah, Italy. And this is at the 43 latitude. And when you go to their lab and you look at their work and their orientation of their gyroscope, they've got it at a 45 degree as well, orientated to Polaris as respectively. And then this is in Germany. And here we are at the 49th parallel, and they also have their device orientated at a 45-degree correction angle to get their readings. So the only publicly available data on single axis gyroscopes readings are this guy's YouTube channel and the what's it called? The Ginger Project. Yeah, so this Ginger Project, these are these labs that have these correction angles. Let me see if I can pull up their paper real quick and show you a configuration. Oh, where you're okay, 1 second. Oops. Yeah, they got it down here at the bottom. Okay, cool. Okay, yeah, so they got their device off axis by 45 degrees so that they can be axially aligned with the sky and or Earth's axis of rotation. And they have it noted here as well. I think, does it talk about the exact angle? But yeah, I was reading through this a couple of times. And they mention that it's 45 in there. Anyway, so those are the only places that have that I could find in the northern hemisphere that have their correction angle. So when they talk about the variance to that correction angle to what they would have to do to maintain being in alignment relative to the latitude, to maintain being in alignment with Earth's axis of rotation relative to the latitude, there's not a lot of data that supports the globe or that like differentiates a globe from a flat Earth in terms of being axially aligned with the sky to measure rotation, right? So, where were we at here? Let me close this out. And I think we were about to watch. Oh yeah, so we're gonna finish. We're gonna let him watch, or we're gonna play him out and do his measurements.
The z-axis towards the South Pole, and this should be perpendicular to the pole, so it should show minimal rotation. The next two are for our negative controls. They face with the z-axis either west or face east, and these will show partial rotations which will cancel out. So flipping from one orientation to the other should lead to a zero result. So the way that we collect the data from this experiment is as follows. The interferometer sits perfectly stationary in a particular orientation, in this case first in the south orientation, and we collect a baseline signal for about 5 to 10 seconds. Then we manually flip the interferometer over to the perpendicular direction and then take another baseline reading. So we've got essentially a baseline, then some noise from the flipping of the instrument, and then another baseline. And this is how we compare the amount of fringe shift which has occurred from one orientation to the other. We can then use the millivolt difference between each orientation and our calibration data to determine the rate of rotation the device is experiencing due to the Earth alone. The negative control progresses pretty much the same way. We start with our baseline on the east-facing configuration, and this is just showing the east-facing configuration here. We then flip it over to the west-facing configuration and do a second baseline for 5 to 10 seconds, and we repeat this process over and over again, flipping from one orientation to another, but keeping it stationary while it's doing the baseline. And then we find out what the average millivolt changes from one orientation to another by doing about 20 to 50 readings. This is just the details of our calibration. We did.
All right, so you take your readings, you flip your device, change your you flip your orientation, you invert it, take your readings, you add them together, average them out, and what he got at the 45th latitude was indicative of a rotation. What was it? 15 degrees per hour when you average it out and add it together, or add it together and average it out at his latitude, right? So the difference on a flat Earth would be that. So on a globe, for one, they say at the equator you're not going to get any reading because you're not going to be experiencing any rotation. There's no evidence of that. There's no one that has any interferometers there doing this to show that. That's just what they assume would happen. Now, as on a flat Earth with a vortex overhead, right, centered at the North Pole, as you get further away from that, the rotational speed has to be faster, right? The edge velocity, as you get further out to the to the edge, it increases, right? So the readings would get stronger. So it wouldn't be this symmetrical situation where you get a reading of like 7.5 that you flip twice or that you read twice, add it out, average it out, add it up and average it out for 15 degrees, it when you get further away, the readings would just increase. So instead of being symmetrical with a globe, and then let me pull this up in a second. So on the glob here at the 45th readings, you should be, they get 7.5 degrees per hour, right? Is what they're equating it to, their fringe readings. So when they're here on the glob at 45, they should also be getting 7.5 as well. But on a flat Earth, right, as you get further away from the North Pole, from that vortex, the readings are just going to be faster. So instead of being 7.5 here, it's going to be like 10 or 12 or something like that, right? Just flat out. And flipping it and taking another reading isn't going to average it out to be 15 degrees per hour. It's going to just increase. It'll be like, just a higher number, right? So, okay, so that was the modern stuff. So this was done. I didn't play out the technical specs on that, so I'm sorry. I'll let him. The audio is so low on it though. He just used like modern stuff. His configuration cost like $1,000 in equipment is what it was. So he had a website here that you could go to look at all the parts and buy the stuff yourself. It was about $1,000. So, and then here he made using a laser printer. He made a device that's about $600 that does the same thing and uses Bluetooth to send the data, so you don't have to stop the device to take the readings or anything like that. So let's see. I haven't watched this in a while. We'll just look at what's happening. So this is a rotating interferometer. So he puts it on the old Lazy Susan,
and you get like a positive change both clockwise and counterclockwise. And this is because we're at phase opposition with the two waves in the stationary state. So in both directions of rotation, you're going to get them going towards closer to phase parity, and that means the voltage is going to increase. So what we've got shown here is the fiber optic gyroscope back on the turntable, but this time we've switched out the multimeter for a Bluetooth data logger, which you can see is the white box in the center. This is a custom designed data logger that we made in-house here, and the Bluetooth transmitter is on the left-hand side. That's a little black.
That custom in-house Bluetooth, dude, very nice.
Box sticking out. So it's ready to go. We're going to rotate this up and send some data directly to our computer, captured in Excel using the PuTTY program, and we'll show the calibration curve for this device. So what we're looking at here is the data logger output that we've imported directly into Excel, and it shows what happens when you start from 0 and speed the rotor up to 105 RPM and then allow it to go back down to 0. So this is our baseline voltage at 0 RPM, which we set to around 0 on the multimeter. And then when it spins up to 105 RPM, we go from the out-of-phase condition to the in-phase condition. So we reach a maximum voltage here at 60 RPM. Then we start heading back towards out-of-phase, which at 105 RPM is the maximum on the turntable. So it just kind of sits there until we turn the turntable off, and then it slowly spins down through 60 to 30 to 19 to 13, back down to 0 RPM. And the red lines are actually some markers that we put in to mark the RPM. So every time the rotor passes a point, each rotation it makes a blip, which we can then see in our data to tell us how fast it was going. And that's effectively what the output looks like. And just note that the output voltage response to RPM is not.
All right, cool. So they're measuring a fluctuation in the voltage, basically, as the device rotates. All right. And then from that, they correspond a rotational value out of that. So let's see, fiber optic interferometer with wireless data collection. And here he's just going over the device and the data curves and all that. Let's see. So this guy he's doing a response to a vertical configuration to an interferometer where a guy said that his vertical apparatus detected an ether as well. And this guy's doing a refutation of that. But I wanted to show, just more fringe patterns, right? So you got your fringes here. Let's see if he shows his device configuration real quick. I think he does. Yeah. So he's got all that. It's going to project the beam out on that where he had the cardboard facing to project the fringe on, and then the camera facing that so he could record the fringes right as it rotates. So. All right, very, very cool. And then we got one more for this guy. Kind of shows how the classic Michelson-Morley setup. So we'll watch this. Actually, I don't think there's any audio to this, unfortunately. So he just goes over the parts of it. So you adjust this. You turn this knob and adjust the mirror, which will put the light beam in phase or out of phase. And then when you have it perfectly aligned and all that, you'll get your even fringe patterns there. And then similarly to how they use the micrometer wire to mark the fringe patterns, to go back and take the measurements, he does the same thing for the calibration. So he marks the fringe there, and then you adjust the do your adjustments, and when the fringe matches the pattern again at the correct width, you're back in alignment, right? So that's the modern renditions of it, right? So now in terms of the readings, real quick, we'll get into quick history on them, right? So the first paper that we read from was Michelson-Morley. Let me close this out. I had it open for 3 days now while I waited to make this video. Go ahead and close this out as well. Okay, so 1887. That's what they were working with. We kind of seen the apparatus and what they were rolling with here. So a lot of this, right? And then we have modern apparati, right? That take, and they're all measuring the same situation. So starting in 1887 with Michelson-Morley, and then moving on to Sagnac in 1913, who did the circular interferometer, which is just, you had a triangle configuration, right, making a circle essentially, and then the device was rotating. And then from 1905 to 1925, we have Dayton Miller. 1927, Dayton Miller did a series of 5,200,000 measurements and tons of controlled experiments that aren't even logged in the data as part of his actual published work. All showing a variance to the speed of light, showing a fringe pattern that corresponds to a fluctuation, right, and not a constant speed, and a speed that actually changes on the equinoxes, right? It follows the motion of the sun. Let's see. So then we got Michelson-Gale in 1925, where they built their big vacuum tube apparatus, and they got that's where they say they measured Earth's rotation as well. And then they completely ignore Miller's work, who, as I show where he mapped out, or what he thought he was mapping out would have been Earth's motion around the sun, right? But they ignore that because it is relative to an ether framework, and it does not give a reading that corresponds to 30 kilometers a second. So we have Dufour and Pruner, who did a circular interferometer, rotating and stationary, and compared them both, and they both give the same reading. And actually, that guy's that one video that we watched, the first one, that apparatus was stationary as well while it got its readings. And we got, is this sorted by year? And then we have Yuri Galev in 2001 and 2002 reproducing Miller's work with radio interferometry and optical bands. And we have Ruyong Wang generalizing the Sagnac effect, showing that linear motion contributes to the fringe shift patterns as well. And we have Hector Manera, who reproduced the Michelson-Morley experiment. They left their device running for 3 years and matched Miller's work. And this is done with modern interferometry. Let me see if they have a picture of their setup in here. I can't remember if they did or not. No, but they were using a modern setup as well. Like equipment that looks like this stuff, right? Like actual, lasers and all that stuff. Let's see, and then we should have one more. Nope, I think that was it. Okay, so yeah, it's been done. It's been reproduced. The work has been, reproduced and all that. So So these effects are reproducible, measurable, quantifiable. And there is an effect, right? That's what they're measuring. That the ether, would is the mechanism that facilitates that, right? That's what causes that variance, right? So with the space time interpretation of the behavior of light, they say that reality is contracting and dilating such that it gives the illusion that C is changing, but it's it's clearly not, and especially with the 2004 experiment here with the linearization of the Sagnac effect, it removes the relativistic explanation of the Sagnac effect of the Michelson-Gale experiment and of Michelson-Morley. It lends it all back to us, and then of course when you analyze the uh, the implications of what Wang did in his experiment, which is what Robert Bennett did here in 2014, shows that the implications again are not only or are that the Earth is stationary with respect to an ether wind, and that there's no chance that because this isn't a rotational effect, right? They attribute these things to Earth rotation and like the Sagnac effect and GPS and all that, and it's uh, not the case. All right, so I hope that answers your questions and gave some insights on the history and evolution of interferometry. Thank you for your time. Let me play my intro and we'll roll it out. All right, turns out my intro is only going to be about 13 seconds. Peace.